squared.
Right. Okay. So let me help figure this out in the following way. I actually need a new page, so let me actually get a new page. Okay. So I got a new page. So let me actually rewrite this formula by introducing an intermediate variable. Okay, the intermediate variable I'm going to introduce is my y hat of I is equal to my axi plus b. So the y hat is my prediction. My gradient, which is going to be my gradient. Basically, this is my y hat, right? My gradient is a summation of y hat of I minus yi equal to 0. Summation of y hat of I minus yi times xi has to be 0, right? And what is my y hat of I? My y hat of 1, my y hat of 2, my y hat of n is equal to, can I represent it as something times my a and b? Remember, my y hat is equal to axi plus b. Yeah, x1, 1, x2, 1, etc. to xn 1. Right? So that's my predictions. All right. And then how can I form this expression in matrix form once I have these y hats in a vector form? So I can also represent my y's, y1, etc., yn to be in a vector form. Right?
Just y1 from so it's x1 minus y1, 1 minus y1.
Yeah, so I can have y hat of 1 minus y1, y hat of 2 minus y2, etc. But how do I form this summation and multiplication of this xi?
Don't you have the data? Xi's?
Yes, how do I represent it in matrix form? Ultimately, I want to...
At the end, you want a 2 by 2 matrix.
Yes.
And then, so in the first row, in the first column, you have just sum of xi. Just multiplying the a.
Why is it not x1 squared? No.
You mean here? So
when you sum them together, when you combine the two equations.
When I combine these two equations,
in one row you'll have the xi squared, and then in the other row you'll only have xi.
Yeah, that's what.
So the task is how can I write these two equations in the ax equal to b form? Actually, a matrix times a and b equal to a right-hand side form.
So because you're multiplying by xi, so it should be x1 squared, and then in the one you would have x1, and then x2 squared.
Right. If you substitute this in, I'm going to have a long formula that is going to give me this. But like here, let me give you a hint. So this one is actually equal to y hat of I minus yi times 1. Right? So basically, I have the same vector summed from 1 to n times either 1 or xi equal to 0.
So have another vector of 1.
Yes. So basically, the first equation is like I have 1, 1, etc. 1, right? times my y1 hat, y2 hat, etc., yn hat, minus the same 1, 1, 1 times this vector equal to 0. My second equation is replacing these 1s with x1, xn times this vector of y hats minus also the same vector of x's times my y's equal to 0. Now do you see where I'm going? This hats is already represented as a matrix form, right? And these two equations can be actually combined into 1, 1, 1 and x1, xn, right? Times y1 hat to yn hat minus the same thing, x1, xn times y1 to yn equal to 0. And the y hats is already a matrix very similar to the matrix we have here. It's actually the transpose of that matrix times A and B. So if I call this matrix to be my big X matrix, then the equation I actually obtained is actually big X transpose, right, times big X A and B, which gives me the y hats, minus, if I call this vector to be my big Y, minus big Y to be 0. All right, so that's actually a different way to write this linear regression problem. So this form actually makes it a lot easier to program, because in the computer, what I need to do is I collect all the data x and y, put them either into matrices or vectors, and in the case I have more than one axis, I just need to add one more column onto this, right? And correspondingly, I just want to add one more column to this, and I have the same form of equation I need to solve. Does it make sense? Yes?
Why can't you just directly put the sum into the matrix? So like, just say like, have a 2 by 2 matrix where like the entries are like sum of xi and then sum of xi squared. You have the data for that. And just calculate that directly.
I can have the data. If I calculate that directly, what am I going to get? So I think I get equivalent formulas of basically this matrix multiplication. For example, if you look at what formula I get when I look at this equation, what is the coefficient of this equation on A? It's actually a summation over I of xi times xi, right? Which is actually the 2-2 entry of this x transpose times x. So the formula, of course, turns out is going to be exactly the same. But if you evaluate the sums yourselves, you wouldn't be taking advantage of all the matrix multiplication algorithms people have already written down. That is a lot more memory efficient than you evaluate the terms yourself.
So if I use like the sum function on MATLAB,
yeah, it'll be actually slower. The reason is actually not so obvious. So the number of operations you count is going to be the same if you do the summation yourself or if you use MATLAB. But the memory access pattern is going to be a lot different. So if you perform the sum yourself, then you're going through all the data from 1 to n every time you evaluate an entry. So there is no kind of reuse of the data you load from the memory. So in a typical computer, the time it takes for you to access the main memory is many thousands times it takes to execute an instruction. And the computers are very smart in the way when they grab a data, they also grab the nearby data and put it in something called a cache. So if you can repeatedly access the same data and do a lot of instructions, you have a much faster program than if you go through the same data multiple times, each time only use the data for one or a few calculations. So the matrix multiplication algorithms that is in MATLAB and almost any linear algebra package basically does that. And it saves you from slower code you would be writing yourselves.
Mhm.